Good afternoon, students. In this lab, we will study about convolution and implementation of matched filter for Barker codes. In preparing for lab 4, you have to read about the convolve function, CONV in MATLAB, and you have to read about matched filtering and Barker codes in the lab manual for project 4. Okay, so in the first part, what we will see how we can implement convolution numerically. As you remember in chapter 2, if I have input xt and system h of t, the output yt is y of t, x of t convolved with h of t, which is this formula from minus infinity to infinity x tau ht minus tau d tau. Now this is a theoretical calculation. But numerically, how can we do this integration numerically? Numerically, we can do by discretizing the time steps. As you know, integration in time domain is summation in integration in continuous time domain is summation in discrete time domain. So we discretize the time step, which is the axis for our case is tau, and d tau is small differential time. D tau will be delta, for example here, and tau is discretized as k times delta h of t minus tau. T is n times delta and minus k times delta. So this will be the summation. So this convolution using the summation numerically, we can do it by this formula, summation from k minus infinity to infinity, x of k delta h of n delta minus k delta. N and k are integers. Now, when we reduce delta, we get better approximation. So when we have smaller time steps, then we will be close to the theoretical result for the convolution y of t. So in this exercise, we will, first of all, what you will do, you will find the theoretical convolution result between x of t, which is e to the power minus t ut, and h of t ut. So first you do this theoretically, and you will find the theoretical result. And that theoretical result, you will plot it. You know how to do it in chapter 2 already. In MATLAB, we make different time steps. For example, delta 0.5, 0.1, 0.01, and we do this numerical summation, okay, convolution. So we check for which time step we get better result. So for example, I will show here an example for delta 0.25. Okay, I have here, I made some small program as you see here. You can take this, you can copy and paste it to MATLAB. I already did it. So I go to MATLAB here, and here I have this one. I copied that result. So this is the convolution. So I have first the time step from 0 to 0.5, the time step until 10, and x exponential of minus t h once from 1 to length of t. Once from 1 to length of t will give you a unit step function. A unit step function, because it will be 1 for every time step. So it will be 1, 1, 1, 1, 1, 1, 1 until the length of t, that means. So unit step function. Note that it is a finite duration unit step function, but theoretically unit step is 1 for t greater than 0. So it is until infinity. Then we have y 0.5 convolution of x, comma h. The convolution of x, comma h will do the summation. Okay, the summation formula, this summation will be done by convolution of x with h, and then this summation, after this summation we need to multiply by delta to get y of t. Okay, that's what I did here. So let's go to MATLAB here. So we have this, and then I plot the function t. T means 0.5 from 0 to length of y minus 1 versus y, or you can take this t is from 0 to 10. And I saved it as the file name lab4 v1. So I call it here in the command window lab4 v1, and let's see the result. You see, this is the result of the convolution. As you see, it's exponential function. Okay, this y of t, this is time, exponential function, and it goes like this, and it stabilizes here. But after t is equal to 10, it starts to decay and it becomes 0. Whereas the theoretical result will continue and settle. Okay, settle as t goes to infinity, it will have some value where you can find this from the theoretical convolution. So why it became decreasing and decayed to 0? Because we make a finite duration signal u of t. That's why. And also exponential of minus t is also finite duration. So we did it from time 0 to 10. That's why it's decaying and going to 0. Okay, but what's important is the result from 0 to 10. Now this I did it for time step 0.25. You will do for the other time steps. You will plot it on the same graph using hold on, and you will compare and you discuss the different results. This is part 1. Let's continue with the other part. The second part, implementation of matched filter for Barker codes. What are Barker codes? Barker codes means if we go to the lab manual here, these are a Barker code, for example, of length 3. Barker codes are having binary 1 and negative 1 value. For example, this has binary 1 between 0 and 2 and negative 1 between 2 and 3. That means when time is between 0 and 2 seconds, it is 1. Between 2 and 3, it's negative 1. And Barker code of length 7 is like this. Between 0 and 3, it is 1. Between 3 and 5, it is negative 1, and between 5 and 6 is 1, between 6 and 7 is negative 1, and so on. Okay, so we have different Barker codes. Barker code of length 3, of length 7, and of length 13. So for what we use this? We use for the design of matched filters. Okay, what are matched filter? Matched filter means you have here an input, for example, a certain signal b of t. This is the Barker code, and you have a system with b minus t. B minus t means the matched filter. The matched filter flipped in time. So it is flipped in time, b minus t. Then what is the convolution of result of this p of t convolved b minus t? If we do some mathematical calculation, then you will find this formula from minus infinity to infinity bt plus tau b of tau d tau. And the result is phi as a function of t. At t equal to 0, this is t is equal to 0, and this will be b square of tau d tau, which is the energy of the matched filter. So for what we use this matched filtering? Matched filtering are used for time delay estimation, because they have very important property. When we do convolution of the matched filter with itself, I mean here the flipped signal of the matched filter, the maximum will occur at t equal to 0 here, at t equal to 0. So that's why they are important for the estimation of delay. For example, they are used in estimation of time delay or time delay in radar systems. In radar systems, for example, they are used to detect the time delay of a flying object such as airplane. When the signal goes to the airplane and it comes back to it's sent from the ground and goes to the airplane and come back to the ground. And we can estimate the time delay. And they are used for time delay estimation, for localization, and so on. Now here is I have one small program which is b of t ut minus 2. That means unit step function which is 1 between 0 and 2. So I have a unit step function b of t between 0 and 2, it is 1, and I convolve it with the flipped part of the same signal. You see here b is this, and then I flip it. How do you flip in MATLAB? You use a function called flip LR, okay, flip right. So you have b and then you flip it, and then I convolve it with itself with the flipped signal, and I used here the time step 0.05 because this is 0.05, and I plot the convolution result, the output of the matched filter, and see where it is maximum. Okay, let's go to MATLAB again. Here I saved the same thing I described here. I just copied this and I took it to MATLAB, and it is this one. I saved it as lab4 v2. You can give it another name. It's the same, and I run this and see where it is maximum. So now my file is lab4 v2. Run it. You see, as you see from this, its maximum is at 2. Unit step function between 0 and 2. Convolve it with the flipped signal, you get this result. So the maximum is at 2. So for example, if it is used to delay time delay, so we will look the location where it is maximum, which is at 2. Now, instead of it is 0, it is maximum at 0. If you see from this formula, I said the maximum is at t is equal to 0. So why it became the maximum at t is equal to 2? Because I have what I call causal matched filter. Causal matched filter means it starts from t equals to 0. Okay, it starts from t is equal to 0. We have a value from t is equal, starting from t is equal to 0. So this is ut minus 2 is between 0 and 2. So if it is non-causal, we can make it, for example, between -1 and 1. But we make it causal from between 0 and 2. So the result will be shifted by 2. That's why the maximum is at 2. Okay, so this is the result of the matched filter. Now, what about if I have a delayed signal, bt minus d? This is a delayed signal, bt minus d. Then the maximum will be at d. You see the result here. the result of the convolution, this one you need to find it theoretically how it is. You need to find it. Bt minus d convolve with b minus t. I get the result phi of t minus d. Phi of t minus d. That means the maximum of this is at t equals to d, where d is the delay. If I have a causal matched filter, then the maximum will be the delay time d plus the length of the matched filter. For example, if the length is 3, so the maximum will be at 3 plus d. If the length is 7, it will be at 7 plus d. If the length is 13, it will be 13 plus d, and so on. So in the next part, I have here a matched filter with length 3 here, and you see I have the matched filter here of length 3, and I see, for example, where it becomes maximum. Let's go to the MATLAB first. Let's go to MATLAB here. I have here, this is a matched filter of length 3. If we want to see this filter, let's plot only this part. Only this part, I will plot it, the matched filter part. Okay. And then plot T versus B3 grid on. Okay, let's make axis from let's say from x-axis is from 0 to 3, and y-axis from negative 1.2 to 1.2. Okay, let's see now the plot. You see this, you can see this one, it is 1 between 0 and 2. It is 1, you see, between 0 and 2, and negative 1 between 2 and 3. Between 2 and 3, it's negative 1. This is a matched filter of length 3. If we go to the lab manual, you see this is a matched filter of length 3, 1 between 0 and 2, and negative 1 between 2 and 3. Now, let's run the MATLAB and see where it is maximum. Again, we run here, I saved it as lab for V3. Lab, let me clear this part, clear. CLC lab for V3. You see, if you see here, it is maximum where at t equals to 3. At t equal to 3, it is maximum here. So that means if I use it for example, delay estimation, because this is causal, I need to consider that it is maximum at 3. So 3 plus the delay will be the location where the maximum point, the location of the maximum point. Okay, now let's go to the last part of the exercise. The last part of the exercise is I have a noisy signal. This signal is called lab4 mis3 signal.mat. And this noisy signal is a Barker code of length 13. What's a Barker code of length 13? Like this. You see, from 0 to 13, I have 1, negative 1, 1, negative 1, and so on. So you can see this one. So this Barker code of length 13, I have it. And there is some delay in that Barker code. That means, for example, if we used it for a certain application, for example, for delay estimation, and if we send the signal from the ground, the earth, then it goes to the, for example, to the sky, and it will hit the target, for example, if it is an airplane, and it comes back to the surface of the earth, to the ground. But when it comes back, there is some noise. So delay plus noise. So it is a noisy signal. and this noisy signal, it is saved in lab4 mystery signal. So in Blackboard, you will go here and you have this one. You have to download this and this noisy signal and save it in your MATLAB folder, okay, in your MATLAB folder, because you will use this. You will load this signal and you will try to estimate the delay. So I have here, I started the program here. I see, I already have the program here already, and I have the Barker code of length 13. So what I will do, I will load that noisy signal, and I have this Barker code of length 13. Then I will flip it because I am going to use it as a matched filter, and I will convolve the noisy signal. That noisy signal in that file, in the file you load, you have what we call noisy R. This is a noisy signal, and you convolve it with a flipped matched filter B13, and you will plot it, and you will find the delay, the maximum delay. And please note that the maximum will occur at, because I have a causal matched filter of length 13, so it will occur at 13 plus a certain delay. So let's, for example, go to MATLAB. I already copied that file, and that means, okay, this file I already copied here, the last part of the exercise, and I saved it as lab4 v4. So I saved it as lab4 v4, and I will run it. I will run and see, we will see where it is maximum. Let me clear CLC. Remember, when you clear, it will clear all the variables so that it will not have, when you are running the program, it will not confuse the program with another variables which might be in the workspace. That's why I start with clear most of the time. For example, here I say clear all, okay, and then this is lab 4, now 4v4, then we run it. Yes, this is a result of the matched filter with the Barker code. So where it is maximum, it should be maximum here, this point you see here at 17. But the exact delay is, we need to subtract the Barker code of length 13, and we should say the delay is this much. So this is an exercise for you. So try to work on the MATLAB files here. So it's a matter of copy and paste in MATLAB, but of course when you copy paste, sometimes you have to rearrange this. I already did here. Also what I need, what I expect from this, I need from you to mathematically prove this. For example, if I have a delayed matched filter, the result will be phi t minus d. So the maximum occurs at d. So can you find this result? So you have to show this, and also you have to show here. Here also the maximum is at t is equal to 0. You have to show this formula, how you find this formula. By the way, this is called the autocorrelation function, because we are correlating the matched filter with itself. So auto means self correlation. So I'm correlating the matched filter by itself, except I flipped the matched filter. So that's one thing. And another mathematical work that I need from you is, you need to find this convolution result, e to the power of t ut convolved with ut, and you have the theoretical result and the MATLAB result for different time steps. You need to plot both and show which one is close to the theoretical result and why it is close to the theoretical result. So you need to have discussions. So I hope you understand this part of the lecture for project 4. This project 4 is expected to be for 2 weeks, this week and the 9th week, and next week the 10th week. So you work on the MATLAB. If you have an issue, you can ask me using Microsoft Teams, or you can email me. So based on that, you will do the report for project 4 for these 2 weeks. And furthermore, you can have always you can use the MATLAB help to get an extra help. You can use here MATLAB help for any function. For example, you can check what is convolve, CONV, and so on, and other functions. How other function here, for example, if I check here, it's a little slow. Here, if I say what is convolve, it will bring you the convolve function. Then you click what's convolve, convolution of U with V, for example, and then the result, and so on. Thank you for listening to this lecture.